Okay, so we're going to talk about AutoComplete. We're going to talk about Copilot. I'm going to kind of show you like a lot of the technicalities when it comes to creating your own. I've gotten kind of far, as you can see right here. Local hello equals YouTube, right? It can get kind of good. There's some bugs there. You saw a little bit, but there's a reason why that's a bug. That's a faked output. Reason why it's a faked output is because I've been using this shared tiny green George Hotz let me have access to, and as you can see, it's currently being completely used 100%, so I don't even have access to the hardware at this current moment while I'm recording this video. So I just created a quick fake request that makes it look like it's doing something. Shut up. Anyways, so check this out. So I'm going to walk through how or what I'm doing and how we accomplish it. So I think the first big thing to understand is, what does it take to build an autocomplete? I know a lot of people always have trouble visualizing how to build software. I've never built one of these things, but it shouldn't be too hard. Effectively, how I think about it is that you're gonna wanna type a certain amount of characters. I just chose 2 arbitrarily. And once we have 2 alphanumeric characters or more, or any non-white space characters or more. Sorry, my autocomplete wouldn't work with white space, the language, but you get the idea. I have 2 non-white space characters. At that point, I'm going to go and I'm going to make a request. It doesn't matter if you're typing or not typing. And then the request is going to have to gather up the tree sitter information, use the LSP to be able to find different definitions. Then it's going to have to ready the request, and then we're going to send the request off to the server. The server is going to process it on all the hardware, and then it's going to send its expectations back. What could I be typing? From there, I'm going to have to then go, okay, I obviously was on, say, position X, and now potentially I'm on X prime because this took a half second. Maybe I typed an extra character. I need to fill in the ghost text, is what they call that, the virtual text, right here, and I need to take off some of it. I need to take off X prime, but if X prime doesn't match what came back, then I need to restart this process again, right? At least that's kind of how I decided to do this, is this like nice little waterfall process. So I don't try to, say, throttle it with a trailing edge. I throttle it with a, debounce it with a leading edge as opposed to a trailing edge. What that means is that if you were to type like X, Y, Z, A, B, I would send off a request here as opposed to waiting for you to stop typing and then send off the request. The reason why I've made this design decision is that I want to prevent what is known as the Copilot pause. The Copilot pause is where you type a few characters and you just wait for the AI to tell you what to do. Instead, I want to make something that instead of being your thought process, instead of being your pilot, I want you to be the pilot. And if it can accurately predict what you're doing, then you will be able to just tab into the thing you're already doing because you are already typing, you're already going fast, boom, you hit that tab, and I wanted it to feel like that. And so that's kind of my whole goal here with this. Okay, so now that we're kind of all on the same page, let's talk about this whole process. So we've typed 2 characters, and then now I need to hit the tree sitter part. And so kind of how I accomplish this is this idea of a pipeline. The pipeline is actually rather simple. All it does is when you make a request, if there is a running pipeline, then I just simply say, hey, pipeline's already running. Let's not do anything. Else, I set myself to running, I set my active state, and then I run this little pipeline function. When this pipeline function returns, I can just set everything to null. I'm not running anymore. Clear any virtual displays just in case there is, and then send back the results in case somebody needs to listen or see what has happened on the outside. All right, so it's pretty simple. To run the pipeline, it's also really, really simple. All I do is I just grab the active node, set it as the active node, and then just do like a nice little recursive async loop here. If we're on a node that is, or if we're on an index that's further than the amount of nodes, we don't keep on going. If calling our node erred, then we're done, right? So I try to have this like nice little loop that we're doing over and over again. And that's it. So that's like the pipeline in itself. So how does it actually work? Well, I have a series of positions I need to be in. Now, the nice part is if you think about this kind of autocomplete that's going on here, it's a very linear approach. Notice I don't have a tree. Now, technically, I could have borrowed the idea of behavior trees from game programming AI to be able to do this in a more robust kind of tree type search, which I may have to adopt. For those that don't know, there's sequence nodes, there's selector nodes, and then there's actual like behavioral nodes at the bottom of these trees, the leaves. And so I could have built up the behavior of this autocomplete via behavior trees, which actually probably would have been the ultimate way to do this. But I realized that I'm just doing a linear walk. I'm just doing a linked list. So I just created the world's most complicated linked list effectively. And so what I do is right when I get my first request, the first thing I'm going to do is I'm going to clear any virtual text just in case there's some other virtual request. I'm going to get my starting location and the starting text line. I am then going to go and say, hey, is there, am I not at the end of the line? If I'm not at the end of the line, I'm not even going to make a request. I'm not going to try to guess what's supposed to be going in the middle of a line. If I don't have enough characters, 2 characters, remember? Again, I'm not going to do anything else. Let's move on to the next stage. Okay, so at that, I'm going to do the tree sitter node. Now, this one's pretty fun. I'm going to grab all the scopes. So what is a scope? A scope, of course, is like a function or the program. That's a scope. So anytime if there's a function in the program, which a program, by the way, is just this file, that means I would have 3 scopes to my cursor. So I use tree sitter to accomplish this. Now, the reason why I use tree sitter is that tree sitter allows you to express what a scope is in a language-dependent, independent way. And what I mean by that is, check this out. So if I go to Cockpit scope, here's my different scopes for Lua, TypeScript, and Go. So if I go into Go, I only have function declarations and function literals. That's it. Those are my only 2 scopes. So if I have a function literal inside of a function declaration inside of the program top level, I'll capture all 3 scopes. And I tag it with this nice little identifier right here saying, hey, anything that matches this expression, that's the one I want to do. And that's for Go. But for TypeScript, of course, they have a lot more scopes, right? There's function declarations, there's going to be functions, there's going to be arrow functions, there's going to be method definitions, there's going to be class declarations. There's a lot more possibility for scopes. And so I have this nice way to be able to do it in a language-dependent way to be able to make the scope grabbing be language independent. And what I mean by that, if I go to tree sitter right here, what I do is I actually go and let's calculate the scopes based on my cursor. So I'm going to get the root tree, so that's the root node. So if I go inspect tree, the root node for any Lua file is just chunk. So that's what's going to come out of that thing is just chunk. And then inside of here, I'm going to get my buffer, the current buffer I am, and then I'm going to attempt to get, whoopsie, that's the wrong one. I'm going to attempt to get the scope query. So that's that scope one. And then from there, I'm going to go over every single node, and I'm just going to order the nodes that match this query that I created by size. So what comes out should be the biggest node to the next biggest node to the next biggest node to the next biggest node. So I'm just going to go through and do that. And then I just double make sure that I have to minimally get 1 node because even an empty file should have 1 node. And obviously I grab the root node right here and I actually set my scope to have the root node in it. So I minimally should have 1. So I kind of ensure behavior should be acting a certain way, which I thought was pretty clever. Hold on, my alarm's going off. My alarm needs to shut up. Get out of here. I understand that it's 9:50. All right, so there we go. So I get all of that, and that's how I do the whole pipelining is that I just grab all the scopes, and then I grab all the imports, because with the imports, if I follow the imports via LSP, I could technically grab all the definitions out of every file. Now, I haven't done the definition tree sitter queries, but once I do that, remember, it's a language-dependent set of things that I can create to be able to be queried in a language-independent way, so I could actually grab all of the references and all the definitions from files using just LSPs and tree sitter, so I could get all that information in like 5 milliseconds, 10 milliseconds. So it's super fast. It's super awesome. So I just do that. So this node, step 2, I just grab all the definitions, my scopes, and my imports. From there, I go to LSP mode. LSP mode simply goes through every single definition based on the import. So I actually get all the definitions based on the import. And a definition, of course, would be for a import would be the whole file. So I actually get out the whole files, and I set out all of the whole files. Now, obviously, at some point, I think it would probably be better to have a second level here where I actually only grab, let's say, function declarations, variable declarations, or maybe only exported stuff, right? I could actually get pretty clever here, but for now, I just wanted to get it to work, so I just do that. And then I go into a ready request mode. Remember, we're just walking through this pipeline. Ready request mode just simply builds up the context, which is all imported files, and then, of course, it builds up the prefix, all the code up until where my cursor's at, and I can send up the prefix, the imported files, my location. I get everything ready to be sent off, and then this is where things get really clever. So how I faked that is because I created a faux request node where I can just pass in something to respond with, and then my responder could do all that information for me. So it feels like it's making a request, but it's actually not. Then I have a request node, obviously, which actually goes out and makes a request to my reverse proxy. So how the reverse proxy works is that obviously Llama or Llama CPP or VLLM launches a local server. So I actually run on top of the local server a Go server that acts as a proxy. So when messages come in, I take my Go server, I could hand it off to specific sets of GPUs or specific local servers. So that way they can be running a bunch of stuff in parallel. So I could actually, even on top of it, do that. I could store context. I could make requests more and more efficient, because obviously sending up all the files and all the definitions and everything is pretty inefficient. But if those files don't change, who says I couldn't implement an HTTP2 kind of HPAC style header caching, if you will, for all definitions on a per connection basis? It actually would not be hard to take up pretty little memory. And that means when you want to do autocomplete, I could send off a singular TCP packet via WebSocket, and that would just be so fast, right? That would just be so much better. So there's so much cool things you could do here to really make this amazing. I just haven't quite got there. This is just proof of concept time still. And then afterwards, I go into this display idea. Now, displaying is pretty difficult because you have your current line of text, right? So let's just say I start typing LO, and then I am going to send off the request based on LO. And then by the time the request comes back, maybe I have LOC for local, but maybe what comes back here, they wanted to type out location, which looks almost like the word local. And then so that way I would have, in virtual text, Asian. And so now I have to, as I type, I have to validate that the difference between when I started and what I have, this chunk falls directly into the estimated text. So it's kind of this hard thing, because the moment I deviate, I have branched off from where the LSP, or not the LSP, from where the auto completion thought I was going. So now obviously I could improve a lot of things here, right? I could have the server respond with 3 separate lines or 5 separate estimated lines, and I could do it as an array, which actually, if you look at the code, I did intentionally do that. I have this thing where I can actually partial match off a bunch of different contents and try to guess the best one. And so that means if I guess a bunch of lines, I could really make this efficient. But for now, this is all proof of concept. I'm working on my prompt engineering, and there we go. And so this is kind of how I designed the program, because the hard part that I was having is like, how do you actually do all of the work to make this all work out nicely in your editor? And what I realized is that this whole request thing, it really is just a linked list. I know people pretend like you never use data structures, but when you program anything worth value, anything that actually creates a moat, as I like to say, you gotta run into these data structures whether you realize them or not. So when you really think about this, when you really look at this right here, initialization node is gonna be a value, which is gonna be a function that needs to be called, and next is gonna be the tree sitter node. And it's going to keep on following that chain until it gets to the end. Yeah, I'm storing it as an array, but really this is just an async linked list, meaning that every single run function gets a done function to call back when it's done. So something like the old style Jasmine async tests before async await in JavaScript. That's kind of how I modeled it afterwards. I could have used coroutines and Lua. I just have never used them. They're a little bit more complicated. I probably could have pursued that a bit more and used that instead of this whole async method, which does lead to slightly complicated programming, but it is pretty easy to use once you kind of abstract it right here. So that means every single node lives in this async kind of world where it actually slowly builds up the information as I make these requests. So it does do the initialization state, it does do the tree sitter, it does do the LSP, it does do the reading of the request, it does do the request, that goes way off to a server, that comes back, I then do the display, and if I hit tab, then my final state is apply virtual text. And so that can actually apply the remaining virtual text based on the starting text, the text I've currently written, and what's left. If I change modes, it can automatically just stop. It has a bunch of built-in stuff that just makes life easy. Anyway, so there you go. That's kind of how I thought about building this piece of software. I think a lot of people, when it comes to these type of bigger pieces of software to try to build, I mean, when I say bigger, remember, I've probably only written a couple hundred lines of code. Find everything, name that looks like star.lua, right? There's only a few of those. I guess I could xargs, cat, that thing, word count line. So yeah, it's only 2,000 lines of Lua. So it's not even that much. And as far as the reverse proxy that I've written thus far is only that. So it's only 2,500 lines of code. So not even a very big library, but even something like this can get so difficult to manage state so quickly because this is a high state mutation operation, right? You have to keep track of so many moving parts because the editor is changing, your request state's changing, your final result autocomplete state's changing. And so kind of coming up with a good pattern is really useful because how I started this, actually, I think there might even still be some of it in the init.lua, is I just programmed everything inside this function, right? I didn't even try. Right here, this little run complete, it had the whole 9 yards in here. And the reason why is that I didn't want to have to try to figure out what I was programming before I programmed it. And this is a huge important point. I created the worst awful code possible here to discover a significantly better pattern later on because I just didn't even know what it would take to program it. So when you're exploring, do not feel bad creating 1,200 lines of absolute slop. You know why? Because those 1,200 lines, they're going to lead you and make you go, okay, I see what we did. Now I can take what I did here and I can create a 10,000 line library pretty easily. That's kind of my goal, is how I think about things. If you've never done it, is that I try to do something that's going to be like a less than 2,000 kind of like library exploration. And from there, I try to come up with a pattern that can shoot up to about 10K. And this is really a pattern you can kind of emulate for really any feature, even in a larger code base, which is you don't have to start knowing everything. Start with something dirty, see all the edges, feel them all out, build that proof of concept. And once you have that proof of concept, it's really easy to write the next one because you don't actually need to do a full upgrade. You only need to do a small upgrade because you're really just copying code over, getting everything done because you've actually already built it, but it's just shaping it into a better API. And so the first day, I just spent just hacking that crap together. The second day, I just reformatted it into this nicer one, and now I feel like I can run a lot faster. Adding in new things is much, much easier, and if I really need to, I already know that I can just simply go to this pipeline, and I can convert this to a behavior tree, keeping the exact same interface, and I don't need to change my pipeline at all. I can actually then do selector nodes, or I can do sequence nodes, and actually walk this whole thing one at a time, and I'm absolutely in love with just trying to create a really good pattern here. And so I hope that you enjoyed this little code walkthrough. This, of course, is on the Vimogen channel. The reason why I do it on the Vimogen channel is that I know that people really like these code reviews. They really like code walkthrough. They want to hear technical stuff. They want to hear how to kind of think through software. And this is just my goal, hoping to kind of make you into a better, more senior engineer, which is really, I think, fighting a lot of the kind of common, maybe past legacy thoughts, which is that you could just design everything by pen and piece of paper, which I don't think you can. Okay, or maybe I'm just not smart enough. To be completely fair, maybe I'm just simply not smart enough to be able to do that because I can't design by pen and piece of paper. I have to see what the problem actually contains. I have to be able to feel it and walk through it, and then from there, I can just crush it. So guess what? The name is the Primogen.